Hey, hello, and welcome to another wonderful episode of the New York City Category Theory Seminar. This week we have Alex Martsinkovsky, who spoke a year ago, 2 years ago, and he's speaking again. Anyways, Alex, take it away.
Okay, thank you, Norson. Today I want to talk about a construct which is called the defect, and maybe I spend a couple of minutes explaining why I want to talk about it and where it appeared. It came into existence a long time ago in the late 60s in the work of Auslander on coherent functors. And it was just a convenient technical tool. And after that, it went into sleep for many years until 5 or 6 years ago when Jeremy Russell started looking at this uh, from a phenomenological point of view. Now, a few months ago, well, actually last year or even before that, I was looking for a tool to help me work in the category of finitely presented functors. The reason for that was that this category is both complete and co-complete. Now, completion, the limits can be computed component-wise, but there was a strange thing with co-limits. Co-limits could not be computed component-wise. And if you can't do it component-wise, you're lost. How do you keep track of a functor? So at that point, I got an idea that the defect could help. I will give a formal definition in a few minutes, but for this lecture, just think of the defect as a shadow of the functor. It does not give,
Alex, are you writing or not?
not yet.
Oh, okay,
Yet.
good.
This is a propaganda part.
Okay, good. We like propaganda.
Okay, yes. So think of the defect as a shadow of a functor, and it's much easier to work with the shadow because it brings you back from functors to modules. Okay. And now that I started looking into that, I was struck by the ubiquity of this construct. And the topic was also taken up by my graduate student, Alex Sorokin. And it actually exploded, the whole thing. And now what I will discuss today is part of a joint project. There will be 4 people in the project, Mamuka Jabladze, myself, Jeremy Russell, and Alex Sorokin. All right. So that finishes the propaganda part, and let me immediately get into action. So there will be 4 parts in this talk. Well, I have to cut them a little bit. We lost a lot of time. So let me start with part 1, which will be fundamentals. So the goal of this talk is actually set up the stage for Alex's talk in a couple of weeks. Alex's talk will be abstract, and I would like to say that my talk will be very concrete. So I don't expect that the audience will understand everything, but I prepared about 14 examples. Probably I won't be able to show all of them, and it's not necessary to understand every one of those. I would be happy if at least one of those would be understandable. They come from different branches of mathematics, so something may play out well. Okay, part 1, fundamentals. Fundamentals. All right. So let me fix the notation. So lambda will be a ring. and that means an associative ring with identity. I need a notation for the category of right lambda modules. Right lambda modules. The target category will be that of abelian groups. And the functors we're discussing today will be additive, they will go from modules to abelian groups. All right. So the terminology. First, I need to explain what I mean by a finitely generated functor, and then I will define the finitely presented functor. When I say I will explain, I will define, all that was already done 60 years ago. So a lot of what I'm talking about today has its origins in Auslander's work. So F is finitely generated if there's an epimorphism from a representable functor to that functor F. When I say an epimorphism, I mean a component-wise epimorphism. We're not in a category yet. Now, we would like to come up with a category of functors. The category of all functors is not going to work. It's just too large. And the home sets are empty in that quote-unquote category. So we need to scale down a little bit. So as a first step, I propose to look at the finitely generated functors, the way I just defined them. And an immediate corollary of this definition and Yoneda's lemma is the following. So if F is finitely generated, then F comma G, these are natural transformations from F to G, is a set for all functors G. Yes, and to see that, we look at the definition of finitely presented functor and home it into G. This way, you get 0, F comma G, going into A comma blank into G, which is by Yoneda G of A, and this is a set, and therefore the natural transformations from F to G sitting inside a set is also a set. So that gives us a hint as to how to build a category. We can just take the totality of all finitely generated functors. Unfortunately, this category is not abelian, and to make life easier, we will introduce finitely presented functors. So here's a definition. F is finitely presented if there exists as an exact sequence from one representable B comma blank to another representable A comma blank to F to 0. So we're modeling our definition on that for finally presented modules. And another fundamental result of Auslander says that the category or the totality of all finitely presented functors and natural transformations between them form an abelian category. So here's my notation: FP mod lambda into abelian groups is an abelian category. So that's our home for the next hour or so. And that's a result of Auslander.
Why did he call it coherent functor? In what sense it has to do with?
Yeah, I call it finitely presented, but they are coherent. If you have a finitely generated subfunctor of a finitely presented functor, that subfunctor will also be finitely presented. And in classical parts of module theory, these are called coherent modules or coherent rings, whatever. That's actually the consequence of that result of Auslander. He showed that when you have a map between two finitely presented, natural transformation between two finitely presented functors, the kernel and the core kernel are also finitely presented. And from this, you can prove what I just said, that a finitely generated subfunctor or finitely presented functor is, in fact, finitely presented. Does that answer your question?
Yes, yes. In other words, it doesn't really have anything to do with categorical coherence or anything like that. It probably was even before MacLean and Ben Abu's definition.
That's right.
Mm-hmm.
Well, that I'm not sure. Auslander published his paper in 1965. Well, maybe a couple of years later, but the conference, the La Jolla conference, took place in 65. So you decide whether it was before or after MacLean's coherence.
Okay.
Okay. All right. Very well. So now we have an abelian category, and the projectives in this category are precisely the representables. All right. Very well. Now let us look at the defining sequence. Here it is. By the Yoneda lemma, this natural transformation is induced by a map on the fixed arguments. So let's have that map here. So we have A going to B by way of small f. Let me introduce the core kernel of that map. And let me pass to the corresponding representable functors. So what do I get? I get 0 going to C comma blank. I'm using the left exactness of the functor home. B comma blank, A comma blank. This is F comma blank. And we know what the co-kernel of F comma blank is from the defining sequence for the functor F. And we have an exact sequence like this. So we have just proved that the projective dimension of the functor F does not exceed 2. And if you're interested, what could it be? The global dimension of this functor category is at most 2, and it could only be 2 or 0. And it is 0 if and only if the ring is semi-simple. Very well. So when we speak about finitely presented functors, you can think of a projective resolution like this, or you can think of a defining sequence like that. So finitely presented functors come from short right exact sequences. So it's good to remember. But I would like to switch gears at the moment and immediately go to part 2 and quickly discuss the Yoneda embedding. So I will introduce the defect via the Yoneda embedding. So here's my notation for the Yoneda embedding. I borrowed the yen sign with an upper bullet. It goes from modules to finitely presented functors and it sends a module to the corresponding representable functor. Very well. So the Yoneda lemma implies that the Yoneda embedding is fully faithful. All right. So what happens then? Well, it takes mod lambda and moves it inside the functor category. So mod lambda will be isomorphic to its image in the functor category. Well, it's not quite precise. It's actually anti-isomorphic. So to make it more precise, I will say that mod lambda will be isomorphic, anti-isomorphic again, to this subcategory mod lambda. And let me put an upper bullet there just to indicate that now I view this as a subcategory of finitely presented covariant functors. Now, the Yoneda embedding is contravariant, and if I apply the Yoneda embedding in to the defining sequence CBA that we had before, what do I get? Well, on one hand, we get the familiar projective resolution of the functor f. On the other hand, well, let us look at the first three terms in the sequence. These are representable functors. So they are in the image of the Yoneda embedding. And that subcategory is anti-isomorphic to modules. So that's an abelian category. So that category has co-kernels of its own. So there will be a co-kernel in the smaller category. And it has to be representable because we're working from inside the module category. And if you think a little bit, you immediately realize that the representing object is just the kernel of that map small f. Very well. So this is the co-kernel of f comma blank in this smaller category. Now, the composition of the last two maps going right and then going down is still zero. So by the universal property of co-kernels, we have a comparison map like this. I'm going to denote it by rho sub f. So this is the comparison map between two co-kernels. On the top, I have the co-kernel in the functor category, and on the bottom, I have the co-kernel in the smaller category, which is anti-isomorphic to modules. Very well. So that leads to the definition. The defect of f will be defined as, well, here's the notation W of f, and that's going to be that representing object, kernel of f. Very simple. So how can you visualize it? It's very simple. You have the map A to B. We call it small f. C was the core kernel. We don't need this, but we're looking at that part here.
It's the kernel of f or the kernel of the P of f?
The kernel of f, small f.
Hmm.
Yeah.
Well, wait a minute, since there's universals, isn't the law of f going to be invertible?
I'm sorry, I have difficulty understanding. Ray, could you speak?
Oh, I just said, if you said it was a universal, the law of came from universal, both are co-kernels, that there, is that an isomorphism or law f?
No, because the top is the kernel in the large category, and the bottom is the kernel in the small, co-kernel in the small category. You have the universal property because the composition of f comma blank and the map going down is zero. So there's no isomorphism, and that is what is
Thank you.
responsible. Is that clear?
Yes, thank you.
Yes.
Thank you.
This
Yes.
is, yeah. So you look at these two categories: the category mod lambda dot and the category of finally presented functors. These two categories have the same kernels, but the co-kernels of these in these two categories are different, and rho sub f is the comparison map. Okay. All right. Very well. So, and why do I call it defect? Remark. Well, that's the kernel of f. So it measures the deviation of this exact sequence from being a short exact sequence. And that justifies, in my opinion, the name. So kernel of f is equal to, quote unquote, the deviation of the defining sequence from a short exact sequence. All right. Any questions? All right. So the first question we should ask ourselves, why is the defect well defined? There are zillions of different presentations of the same functor capital F. So how do we know that it's independent of the presentations? Well, you can do it the pedestrian way, simply by following definitions. And well, how would you prove that? Well, you can think of this way. Actually, let me not dwell on this. Instead, I'll show you an elegant way of doing this. So let me ask a question first. Why is W of F well defined? Why is W of F well defined? And the way we're going to prove this will actually provide us with a lot more information than what I just said. So to answer this question, I'm going to look at the map rho sub f, that natural transformation, the comparison map. So what can be said about it? The first thing is that rho sub f is an isomorphism on injectives. Because homing into an injective, if you look at this fork at the top of your screen and you put in an injective in place of the blank, homing into an injective is an exact sequence. So you will get two core kernels, honest to God core kernels, and therefore they will be isomorphic. All right? So that proves the first claim that rho sub f is an iso on injectives. And my second observation is equally brilliant, that kernel of f comma blank is left exact. All right. Now, kernel of f, I remind you, is that W of f, capital F, that is. All right. Now, when you look at these two properties, then you have to go back to Cartan and Eilenberg and dig out a statement that these two properties uniquely determine the zeroth right derived transformation for the functor f. So this implies that rho sub f is the zeroth right derived transformation. In particular, the target kernel of f comma blank is the zeroth right derived functor of f. Once again, kernel of f is W of capital of f. Okay, so W of f represents the zeroth right derived functor. Along the way, we proved that the zeroth right derived functor of a finitely presented functor is representable, and W of f is the representing object. So that settles the question. Why is the defect of capital F well defined? Because that's the representing object. Well, let's squeeze a little more out of this. How do you actually extract W of f from the zeroth right derived functor? Well, just use the Yoneda lemma. So, and that gives me an alternative definition. Namely, W of f is the natural transformations from the zeroth right derived functor to the Yoneda embedding of lambda. So let's decipher this. What is it? R naught of f, as we agreed, is W of f, comma blank. And you map it into the Yoneda embedding of lambda. So this is lambda, comma blank. And you now use the Yoneda lemma, and that's home lambda into W of f, and that's exactly W of f. Very well. So here's our alternative definition. And at this point, I could actually stop this lecture because I promised to give you a definition that works for an arbitrary additive functor. And here it is. The right-hand side does not remember that f was a finitely presented functor. So now we see how to define the defect of any additive functor. So I could stop right here, but I don't want to stop here. I actually want to continue, and there are two reasons, at least, to continue with this construct. The first one is that we can do even better, and that will come up at the end of the lecture. And the second reason is that I want to give a lot of examples. As I said, I prepared about 14 different examples, and I would like to demonstrate at least some of them. They come from different branches of mathematics, and maybe some of them would appeal to the audience. By the way, it's not necessary to follow all the examples. They are independent of each other. So if you are averse to examples, you can go to sleep and I wake you up before we get the even better definition of the defect.
This definition is yours, or this definition it goes back to Auslander, or what?
This is well, I could say it's mine, but it's a triviality. The next definition will be also very simple, but it's not immediately clear. This one is immediately clear, right? All right. Okay.
Yeah.
Very well. So a corollary of this alternative definition is that W is an additive countervariant functor. All right. From where to where? It goes from finitely presented functors to abelian, from modules to abelian groups, back to modules. So I want to start with a picture like this. Mod lambda on one side, FP mod lambda on the other side. We have the Yoneda embedding. And a path back given by the defect. Okay. So The first proposition that is needed is that W, the defect as a functor, is left exact. Why? Well, just look at the formula, the frame formula at the top of your screen. So what is W? W is the composition of two functors, blank y dot of lambda composed with R naught. You need to know that R naught is a right exact functor. And the reason for that is this because it has a right adjoint. The adjoint being the inclusion of this finitely, well, representable functors into finitely presented functors. Okay, therefore, R naught is right exact. And the next functor is left exact. So when you do the combination, you get a left exact functor. All right. So that was easy. And the next important thing is that the defect evaluates to an isomorphism on the comparison transformation. All right. Why is that? Well, the reason for this is that if you apply R naught to rho sub F, that will be R naught F to R naught F is an isomorphism, always an isomorphism. That's an isomorphism. The reason for that is that, as I told you, rho sub F is an isomorphism on injectives. And since the homology groups are defined in terms of complexes of injectives, you automatically get an isomorphism when you apply compute R naught. And now just plug it in back into the definition, and you get the desired isomorphism. All right. So that was the end of part 2, and now let me switch to examples. So this is part 3, actually. Examples. The first question we should ask ourselves, when is the defect 0? Well, the answer is immediate. We already know it. It's the kernel of F has to be 0. That is, F is monic. And as an application of that, let's look at the functor capital F given by x1. Well, for the module A, I take a projective mapping onto it. The first syzygy module is denoted by omega A, and I apply the Yoneda embedding. So what do I get? I get P comma blank going into omega A comma blank. I am now inside the long exact sequence. The next term will be x1 A comma blank, then x1 of P, but P is projective, so that's 0. And lo and behold, you have a projective presentation for the functor x1. So if you call, say, this iota, then the corresponding natural transformation is iota blank. So x1 is finitely presented, and its kernel, the kernel of iota is 0. So the defect of x1 a comma blank equals 0. That's our first example. Well, but there's a more general result. So more generally, we have the following criterion. The defect of f equals 0 if and only if, and that may come as a surprise, the f vanishes on injectives. Now, we don't have much time, so I'll skip the proof. I will just say it instead of writing it. So if you have defect equals 0, that means the sequence above 0 to a right here. This sequence is exact, and when you home it into an injective, it remains exact. So the corresponding functor will then vanish because it was defined as the core kernel, but since this sequence is exact, the functor will vanish. So that is easy. Going backwards, if you want to show that the defect of the functor is 0 if it vanishes in injectives, well, remember, f and its zero-derived functor have the same values on injective. So if f vanishes in injective, the same is true for R naught of f. But that's a representable functor. It's represented by the defect. So if it vanishes in injectives, so take an injective envelope of the defect, and then home from the defect to its injective envelope has to be 0. That means the defect is 0. That's it. So we're done with this. By the way, this gives us another proof that x1 of a comma blank has defect 0. Why? Because this functor vanishes on injectives. And I like this proof better than the first one. Why is that? For the first one, we needed the existence of projectives in our category. We are working with modules, so this is not a big problem. But if you switch to more general abelian categories, for example, Grothendieck categories, then what? You may not have enough projectives. However, you do have enough injectives, and the second proof would still work. All right, so much for the functors that vanish on injectives, which is the guarantee for the vanishing of the defect. Now, let's look at examples when the defect is not 0. So we'll take a representable. So what's the presentation? Very short. A going to 0. That's our f. The kernel of this is A. So if A is non-zero, you get a non-zero defect. So this is non-zero if A is non-zero. I love my tautologies. All right. But again, there's a more general perspective, point of view. Let me phrase it as follows, as a proposition. Suppose you have a non-zero functor with projected dimension less than or equal to 1. Then I claim that the defect of this functor is non-zero. And maybe here we'll go through the proof. All proofs are very short, by the way. So here's a projective resolution of the functor of project dimension at most 1. So b comma blank, a comma blank, f. So this is small f comma blank. Very well. Now we see that f comma blank is monic. And that implies, by the left exactness of the Horn functor, that f a to b is epic. All right. Because our functor is non-zero, f, small f, cannot be an isomorphism. F is not an iso, and therefore there must be a kernel. Kernel of f is different from 0, and we're done. So the defect is different from 0. Now, this has interesting connections with logic. Well, I wanted to say mathematical logic, but actually we could be more specific. It's a connection with model theory of modules. The functor x1 a comma blank cannot be given as a solution set or a projection of it of a finite system of linear equations. So what is going on here? Well, you look at the at the language of modules. What do we have here? We have the equal sign, we have the 0, we have the multiplication sign, scalars by elements of modules. So we have unknowns in the module, and we have letters for the elements of the ring. So if you look at what is called what is it called? Primitive positive or positive primitive?
Positive.
Positive primitive formula. What is it? Well, suppose you don't even have the existential quantifier. All the components that you just mentioned amounts to a linear equation. And if you use the conjunction symbol, then you have a system of linear equations. So one thing to remember, that when you have this system of linear equations, actually it's not a system, it's a symbol for a system, which you could apply to a module. And every time you apply it to a module, look at the solution of the system, you get a solution set. The thing to notice here is that this solution set, unlike the case of linear algebra, where you worked over a commutative ring, that is a field, this is only an abelian subgroup. That's the direct consequence of non-commutativity, general non-commutativity in the ring. So what you get is, let's say you get a rule. If you give me a module, I will give you a solution set, which is an abelian group. So that's a functor. In fact, it's an additive functor. Now, if you want to throw in an existential quantifier into your system, then geometrically that amounts to a projection of the solution set away from the existentially bound variables. Okay. Now, the functors that arise this way all have projective dimension at most 1. And as we just showed, the defect of such a functor has to be non-zero, but x1 has a 0 defect. So x1 cannot be given by a system of linear equations or by a solution set of a system of linear equations or projections of it. And I found in my pressed book a wonderful theorem. I forgot who proved it. That I already mentioned the first part of it, that the projective dimension of such functor is at most 1. But then the other part says that the existential quantifier can be eliminated if and only if the corresponding functor is representable. So the functors are clearly connected with a model theory of modules. Okay, so that's how much I wanted to say about that. And now I want to move on. The next thing will indicate connections with universal coefficients. Well, here, lambda is again an arbitrary ring. C is a complex of lambda modules. I can take a home from the complex into coefficients. That gives me a functor, C comma blank. All right. And one thing to check, and it's very easy, straight from the definition, that if you take the cohomology of the resulting complex, it's always finitely presented. Here, n is some fixed number. We just concentrate on the cohomology in a fixed degree n. And now, if you remember the universal coefficient formula, 1/2 of it constructs a map. In fact, this is a natural transformation if we adopt the functorial point of view, which goes from this functor to the dual, or I should say home, from the homology at the nth place into blank. Now let's look at this map rho. What can be said about it? First of all, as we learned in topology, rho is an isomorphism on injectives. And another instance of a brilliant observation, the target is left exact. So this implies that the right-hand side is R naught of the left-hand side. And therefore, we remember that R naught is represented by the defect. So the defect of the functor Hn C comma blank, the cohomology functor, is isomorphic to the homology of the original complex. I don't know if I already mentioned it. Many things that I am discussing today are really low-hanging fruit, and they are virtually trivial, including this one that you showed. It just, how many people view the universal coefficients theorem as a statement about functors? But here's an example. All right, so maybe a colloquial statement to accompany this is that the defect of the cohomology functor equals the value of the homology.
It's some type of duality. The whole thing is a duality. The duality between, I don't know.
Yes.
This is like
Yes.
the Ekman-Hilton duality or something like that.
Yes, and yes, Alex will have quite a lot to say about dualities. There are, and we're not there yet in the sense that certain dualities like the Poincare duality, local dualities, and local algebra, they still have to be explained. But I'm glad you mentioned dualities, because if you think that this is the last word about the role of cohomology and homology with regard to the defect, then I will show you another example where you will see that the opposite is true, that the defect of homology will be a value of cohomology. So very curious. Norson, please tell me how much time I have.
I don't remember when you started. I guess I don't know. How about 10
It
minutes?
doesn't matter. It doesn't matter. Everybody is tired today.
Right,
So at 7 o'clock was the official time, right?
right.
So I should end at 8:30. Is that the how you go?
Definitely, definitely.
Yeah, yeah. So I have another 15 minutes. It looks.
Okay.
All right. Okay. Now next, I want to indicate connections with Auslander writing theory. So now I'm assuming that lambda is a finite dimensional algebra, or even more general and Artin algebra. If you don't know what it is, just think of a finite dimensional algebra. And I have a non-zero module, and I assume that it is indecomposable. Cannot be broken as a direct sum of two modules. A remarkable property of Artin algebras is that associated with this module M, there's a simple functor denoted by S sub M. Simple functor associated with M. And it has the following property, that Sm on N equals 0, where N is indecomposable and N is not isomorphic to M. In other words, S sub M will be a non-zero functor which vanishes everywhere on all indecomposables except for that chosen module M. Okay? So now let us look at two cases. Case one, when M is not injective. M is not injective. Well, but then away from M, you get all the injectives, and S vanishes on the injectives. So that tells me immediately that the defect of Sm equals 0 because it vanishes on injectives. Sm vanishes on injectives. All right, good. So it comes from a short exact sequence. Sm comes from a short exact sequence. And what short exact sequence is it? That's precisely the Auslander writing sequence. So this is the almost split sequence. Almost split sequence. Now, if you want to fill a gap in your education and quickly learn Auslander writing theory, you won't find this approach to Auslander writing theory because Auslander intentionally suppressed the functorial origins of the theory. He was afraid that the audience would not like functors. But that's how the whole theory came into being. This is the origin of Auslander writing theory. Case two, when M is injective, then the minimal projective resolution of M has projective dimension 1, and as we know, the defect will be non-zero. And in fact, the defect will be precisely what is known as the circle of the module M. So that's the sum of the simples contained in the module M. The next example will deal with the tensor product. So what is the defect of A tensor blank? Well, in order to ask this question, we have to make sure that A tensor blank is finitely presented. That does not always happen, but Auslander supplied us with a criterion. So A tensor blank is finitely presented if and only if the module is finitely presented. Okay, so let me assume that A is finitely presented. Then it turns out, and that's really easy to show, that the defect of A tensor blank is the dual module of A. And this has very interesting consequences. Well, first, let me record a trivial proposition. If A is finitely presented, and the dual of A happens to be 0, then A tensor blank has defect 0. And what does that mean? That means it vanishes on injectives. And here's an application. I stated as a corollary. Well, suppose that the Jacobson radical of lambda, and let's look at lambda as a right module of itself. Suppose it is finitely generated. And also let's assume that the circle of lambda as a right module is 0. So the circle is the sum of the simples. It is also the left annihilator of the Jacobson radical. So left annihilator of the Jacobson radical. Then we have a rather unexpected conclusion. Then every non-zero injective left module is infinitely generated. What's the proof? Just one line. We're going to set A to be lambda modulo the Jacobson radical. Because we assume that J is finally generated, A is finally presented. Okay, and the dual of lambda mod J equals 0 because that's exactly the circle. Okay, and then the proposition tells me that lambda, sorry, the proposition tells me that lambda mod J tensor any injective equals 0. And now use Nakayama's lemma. Nakayama's lemma implies that the injective is infinite. That's all. All right. Now, in the remaining 7 or so minutes, I would like to quickly skip to the Yoneda lemma. So in my talk, this is number 9. So the Yoneda lemma and friends. And so what is it? The statement is that the Yoneda embedding and the defect form a right adjoint pair. So in detail, F, natural transformations into the n of A is the same thing as A into the defect of F. And that is natural in both F and A. And the proof is an easy exercise. Oh, excuse me, let me close my door. And then the companion lemma, so this is lemma 1, and then there's lemma 2. If you take the zeroth left derived functor of the Yoneda and bring back the defect, then this is a left adjoint pair. Form a left adjoint pair. All right. So in detail, this means L naught y yen of A into F is the same thing as the defect of F into A. And again, this is natural in both F and A. So what does that mean? That means that the defect is a contravariant by adjoint, and therefore it interchanges limits and colimits, and in particular, it is exact. All right, so here's the picture. Once again, you may recognize it. We had mod lambda. We had the finitely presented functors on mod lambda with values in abelian groups. We had a way of going from left to right by the Yoneda. We can come back by the defect, or we can go forward again by the zeroth left derived functor of the Yoneda. And so what have we said? That the former pair is right adjoint. Here's our notation for a right adjoint pair, and this will be our notation for a left adjoint pair. All right. Now, I'm skipping examples of yeah, maybe I should make this remark just, I'll just say it. Since W, the defect, is an exact functor, if you look at the functors with defect 0, then you immediately realize that that's a Serre subcategory inside the finitely presented functors. So now we have the ambient category, finitely presented functors, and then we have the subcategory of functors of defect 0. This is a Serre subcategory, so we can form the Serre quotient. And the remarkable result of Auslander is that the corresponding Serre quotient is equivalent to the original category of modules. So the upshot is that there's no loss of information when you pass from modules to finitely presented functors. Very well. And in the remaining couple of minutes, I want to do what I promised, and that's part 4. Part 4, how to generalize the defect of arbitrary additive functors. Arbitrary additive functors. So to this end, let me revisit the Yoneda lemma. So I remind you that that's the statement that F into the yen of A being isomorphic of A into the defect of F. And please allow me to use my eraser as a teaching tool. So I'm going to erase the letter A and replace that with a blank. So, and I'm going to look at the left-hand side and I view it as a functor of A, or of that blank. So what can be said about this functor? We can make two observations. Number one, so the left-hand side is left exact because it's a composition of the Yoneda embedding and then the covariant home. Both are left exact. And the second observation is that the left-hand side moves coproducts to products. And now a remarkable theorem of Watts kicks in. So Watts tells us that the left-hand side is representable, and it's represented by its own value on the ring, on lambda. So the left-hand side will be isomorphic to f, the yen on lambda. And I put a blank here. Here we go. Do I have enough parentheses? I should have 3. Yes, here we go. So once again, it's blank f into y of lambda. All right, but we know it's represented by the defect, and it's also represented by this. So we now recover a new definition of the defect, this being f, the Yoneda of lambda. And that's the improvement over the original attempt where in place of f we had the zeros right derived functor. So now this works for any additive functor, and you can use it without any mention of the zeros right derived functor. But if you like the right derived functor, you can still replace f with its zeros right derived functor. And with this, I think I have to stop.
Thank you. Thank you. Well, you can't say it's an abstract result. I mean, whatever. You had a lot of different. It shows up a lot of different places. Very nice.
Yes.
I like the fact that you don't see an adjoint to the Yoneda embedding. You think of it usually as, it's exactly not that, but very interesting. Anyways, thank you. Any questions? Any discussions?
Yeah, I have a question. Do I understand it right that PP formula is considered as functors?
Yeah. Oh, Philip, could you speak up? I can barely hear you.
Okay. Yeah. So, do I understand it correctly that a PP formula considered as a functor, right? Is
yes
never has defect 0 unless it's trivial, right?
That's right. That's right.
So what is the defect of a PP formula?
Well, what is the defect of the PP formula? You have the presentation. It's a project dimension 1, so you have just a map between two projectives. So it comes from a map on the fixed arguments. Just take the kernel of that map. That's going to be the defect. You may not have an interpretation of this inside the PP formulas,
right?
because this, for example, this may not be even a finitely generated module.
Right.
But it indicates that one has to work in a larger category where the defect will have an interpretation.
Any other questions? Anyways, so again, Alex Sorokin is gonna speak next week on.
I think he will speak in 2 weeks.
No.
On the 27th.
No, hold on. We'll check.
We're on break next week.
Right, I know, but I thought we pushed it in. Hold on.
Yeah, it is scheduled. Well, on the homepage, it is scheduled for a week after.
I'm sorry, you're right. I'm wrong. So Alex is going to speak on April 27th. Thank you. Okay, so in 2 weeks. Anyways, we look forward to seeing everybody. And I'm sorry for the confusion in the beginning, but welcome to the Zoom world. Anyways, thank you very much, everybody. It's a pleasure. Alex, if you can send me the recording, I'll put it up as soon as you can. I don't know how you're going to send it to me, but you can share a link or something.
I will share a link, absolutely. It will be ready in about maybe 15, 20, 30 minutes.
No rush. Whenever you send it, I'll put it up. Ladies and gentlemen, it's a pleasure. I hope to see you all in 2 weeks, and we will talk. Take care.
All right.
Take care. Bye.
Thanks, Alex.
Thank you. Thank you very much.